We're going to be a little bit overwhelmed because you've got two of us today to teach you through this. So we've got Jeremy. Do you want to share your screens and show your beautiful face?
Hello, I'm like looking at that. Hello everyone, I'm Jeremy. I'm going to be taking the presentation part where, as we are joined in the lab by Kat, Alex and Etienne, who will be doing the...
Can you for a minute? So we're just going to share and introduce ourselves.
Right there now, Ned. Cool.
There we go.
So we should have, Kat, we should have 9 in there now, I think.
Yep, we got 9.
9, good.
So you can see Etienne, give us a wave behind.
There's that in.
And then you've got Alex as well again. All right, so we're going to start the session with Jeremy. So he doesn't have a permit to be able to come here today. So he'll be teaching from a lovely area of his home. We're going to mute and we'll be helping from behind the scenes. Over to you, Jeremy.
Awesome. We have 10 here, 11 with Etienne joining us. So, yep, I'm Jeremy. I'm going to be taking the actual presentation aspect, and Kat will be doing all the lab demonstration. So, welcome to Unit 2, Analytical Chemistry. We're looking specifically at analytical water techniques. And I was just wondering quickly, before we get on, there are 2 things I need to know. Do you have graph paper and a pen and ruler handy? Because we'll be doing a calibration curve later. And also, how did everybody go with the pre-work?
You're allowed to speak.
We all have graph paper and a pen, and I can't speak for everyone on the pre-work, but yeah, it's all right.
Awesome. Well, hopefully everybody found it all right. Like, it shouldn't really well for this, and if you ever need any help with it, you can always just go back through the modules. Anyway, without further ado, let's get into it. So, this is Collaborate. This is our communications platform.
Jeremy, we're just fucking up a poll. We're a bit slow today, sorry.
Oh, no, you're fine.
Just before you continue on.
Yep, all good. So, we just poll. Okay. Okay, awesome. So, we got most people smashing it, most of you doing a part of it. I can appreciate that. That's a good effort. And if you've only done a part of it, you should still be able to follow along. Hopefully you've covered this stuff already in your classes. So, without further ado, this is the program we use to communicate. It's Collaborate. Down here, you'll see a little person. Yours probably will just be like a little blank face, blank postured person. That's okay. So if you click on that person, you're able to tell us if you agree, disagree, how you're feeling. If everybody could just show me how they're feeling today. Okay, we got a few happies and agree. Awesome. Thank you. Okay, so moving on. You've probably already found it. I think I skipped too far ahead. Yeah. If you click that little purple arrow down there, it will let you participate in our little chat function that we have. And when you bring up the chat function area, it should look like this. So you just can type into the chat to us to answer questions. It's good to participate, but you also have your mics and you're more than welcome to use it. Also, one more thing, you can also click this button down here to raise your hand if you have a question. I might ask you to raise your hands later on just as a check for certain things. That's all right, and we'll get there when we get there. So, without further ado, I just want to know one thing. Could you tell me what you think all of these images have in common? Nice use of emojis, Edian. There are no right or wrong answers. I just want to know what you think about these images. Feel free to type it or feel free to use your mic to tell us. Atoms. Oh, actually, yes. Atoms is technically correct. There are atoms present in all of these. So this might have been a bit ambiguous because obviously we got a picture of an open-faced mine, some honey, some sports, and an explosion. It's very weird to try and connect all of these. But actually, all of these are related through analytical chemistry. For example, we can use analytical chemistry to measure mining runoff in water. We can also use it to determine drug usage in sports through HPLC. Like we can test blood, urine to see if people are cheating in sports or if people are feeding animals these to help them win. This is actually very relevant considering we had the Melbourne Cup yesterday. So we also have explosions. We can look at explosive residue in water and soil samples, which helps us determine if something was maybe arson or if it was actually an accident. And lastly, this one's a bit more complicated. We can look at honey, and we can actually look at if people are making something like fake honey, because honey has certain sugars in it that can't be replicated by putting syrups and stuff in there. And that's done through a technique, NMR, which is nuclear magnetic resonance. But you'll learn more about that in year 12. So, without further ado, I'm going to get Kat to do a demonstration on UV vis. And before we move on, can someone tell me in the chat or through their microphone what UV vis actually stands for? Close. So ultraviolet is correct. So remember we type it out like this. And well, at the end we'd normally say spectroscopy. So it's actually ultraviolet visible spectroscopy. And now Kat, if you could share your setup.
Here we go. So here is our UV vis. So I don't know if you have one of them, a bit smaller ones at school, like a colorimeter one, which you can see, as you can see, we've got a setup here with a nice color change. And how we actually use these is this tiny little thing here called a cuvette. Now, how close do I need to go? All right, and you'll see on one side it's really clear, and on the other side it's really fuzzy. So when we need to put it into our machine, we need to make sure the clear side's going through because we're having a beam of light travel through it. If we were to put the beam of light on this side, it would scatter it. So it's really important. You also need to check that it's clean, check that there's no cracks in it or anything like that. So here we have our little machine, and with gloves on I always find it really hard. You have here this nice little arrow here, you have an arrow on here. And that basically is a bit of a hint for you guys to know when you're using it as to which way you need to put it in. So we turn it on and we have some Terrible's 80s music. Oh, go ET, he's got the dance on. Here we have our little cover, and simply you can just take that out there. So I'm going to use the Spectro. There are lots of different ones you can do. You can use this particular machine for DNA as well, which is pretty crazy. But before you get to do anything fun, you can set this up to do a beautiful calibration curve. In this case, I'm just going to do a photometric one, which just does our concentration. So I need to set this up. Now, I've got a bit of a question for you guys. And this here is the colour red, as you can see. And it's a nice little colour range we have. But can anyone tell me, because when you use this machine, you need to use the different, on the colour wheel, the opposite side. Can anyone guess what is the particular colour we would require in our colour wheel if we're using red? Oh, good guess, not blue. Very close. Yes, you are right with that. It is green. So for us, we need to set this up and have it at 550 nanometers. So green is a bit of a range there from about 450 to just over 550. So for our colours, we're just going to be using this. I'm only going to be using one wavelength. So it's all pretty sweet now. So you go enter. What are you doing to me? We'll call it test. This is why I use this, because it lets me do this nice and well. I don't want to save it. That's what my problem is. Okay, all good. So now the first thing, in this case, it's just distilled water. So we're just going to be using our blank. So we simply chuck that in there and we're going to hit our 0. And that gives us our reading, which has background noise in a way, and that's what you're going to be classifying all your colours. In this case, we have 0, which is, and then what you would do is go through each of the different colours and get your different concentration. And depending on what setting, the machine can do a calibration curve, or you can make your own. So I'm going to do the really bright colour red one here. We're going to do a run, so we're going to read this one. And so it's measuring at the, and we get our absorption reading, because as that light carries through, you'll get what light can't get through will be our reading. So we got it at 3.307. If I was to go through all the different colours, you would see that we'll be getting different readings through. So I'm going to hand back to Jeremy now. That's a pretty cool machine. And there's lots of different things you can do with it. Take it away, Jeremy.
So, sharing my screen again. Here are our actual learning intentions, not just for today, but for the entire analytical water techniques module that you'll do, which includes the pre-work today and the post-work. So, by the end of it, you should be able to experimentally determine potential hazards using the analytical chemistry techniques we're talking about. You should also be able to contrast the differences between the three techniques. And you should also be able to use calibration curves with these techniques to determine concentrations of unknowns. So, one last thing, we're not actually in the lab today. Well, Kat, Alex, and Eddie are. But if you are, there are simple safety rules you have to follow. I'm not going to go through them with you, but we do have a quick poll question about safety. So I'll just say it out loud first, give Eddie a chance to catch up. If you spill acid in the lab, what should you do? Just waiting on Isabella and Mia. Fantastic. Everybody answered, and you all got that correct. Yes, you should notify your teacher or your lab tech. They're both very knowledgeable, and they can help you and make sure that nobody gets injured or gets acid on them. So, yep, just after having a quick read over these, they're just standard lab rules. If you were at KIOSC today, which I wish you could be, because then you could play around with machinery, then you'd actually have to abide by these. But luckily, you're in the classroom. So, we're now going to actually start talking about the main focus of today. But before we do that, I just want to know in the chat or with your microphones, what effects can companies have on the environments around them? I'll give you about 36 seconds to answer this. Pollution's a great answer. Pollution is a very big thing with companies and their environments. Any other answers? Destruction of habitat, that is a great one. Yes, companies are often destroying habitats of local wildlife. Any other answers? I mean, we're all on the right track here. Yeah, there's also contamination from the waste that companies produce and disposing of chemicals. Fantastic. So that's actually what we're going to be talking about today. So we're talking about a lake in Western Australia. It's called Lake Argyle. Lake Argyle, has anybody actually been there? Agree or disagree? I know Kat has. Amelia, you have. That's awesome. So majority of people from what I'm seeing have not been. So just a quick little spiel about Lake Argyle. It's quite a big lake, Western Australia, yep. It's dammed off, there's a township below it, and there's actually a diamond mining company very close to it. So we will be talking about a diamond mining company, but there's no association. This is just a scenario. So, recently, animals around Lake Argyle have actually been appearing less lively and have actually been dying. The locals are trying to blame some of the companies that have started up around the area. There are 3 pharmaceutical companies they're worried about, and the mining company. It's our job today to actually determine who's at fault and what is causing the animal population decline at Lake Argyle. So, the mining company. Mineplex Infinity is a diamond mining company. Through their diamond mining, they're actually contaminating the lake with an unknown metal. What analytical technique could we use to determine the concentration of a metal? I'll just give ET a few moments to put the poll up in the chat. Okay, so while we're waiting, yep. There's also another thing we're worried about with metals. Metals bioaccumulate. So fish ingest them or other animals, and then those animals get eaten, and then that eating animal, oh, okay, we're getting some poll answers in. So that animal continuously eats that food source, and it gets more and more of that metal in its system. And then other animals eat that, and slowly metal starts to build up it's higher in the food chain, causing metal poisoning. So everybody's answered, and it's AAS. You're all 100% right. Now with that, what do you think? What does AAS stand for? Give you a few Fantastic. I would accept both of those answers. So I'm going to pass it back over to Kat, who's actually going to do a demonstration of our unknown. I want, for this demonstration, I actually want you to record the colors of the unknown and the colors of the knowns so we can make a good comparison. So back over to you, Kat. I'll give Kat a moment to catch up.
Just setting up now.
Okay, awesome.
So here comes the camera.
Where are we at, guys?
Just at the AAS. Okay, did anyone give us what the AAS stood for? Awesome work. All right, so here we have our AAS. So I'm just want to show you, we've got our gas lines here, and that feeds it into here. So we have our burner set up here. And what happens is we have our sample that is sucked up into the machine, and then with our gas burning here, of course I don't have it alight while my fingers are in it, it then will burn that substance. If there's a metal present, that's where you'll get that it being excited, and when it gets excited, that means that we'll have colours coming out, our electrons moving around. Over here, let's get Alex to come around so I'm out of the way. You'll see that there is one little lamp in there, so you just need to get in a little bit. And that lamp there allows us to have the light going through when the flame has the colour come through, and then we get our absorptions. And then from there we can make our calibration curves to work out how much of that particular compound is present. You can also use it just to identify what metals are present. So the first thing we're going to do is light this. Of course, when you get your detection, you have your computer over here that tells you what amounts there are. Okay, so we're all lit now. And what we're going to do is start with our unknown, and then we're going to go cross-reference it with our knowns. And you may see there's a bit of a different colour there, give you a bit of a hint that maybe that's not the right one. So we just have distilled water each time because we want to flush out the system. So has anyone done the flame test at school? So here's our unknown. Take note of its colour. See, it's just lost a little bit. So you see the colour there? So take note of what that one is because you need to know what it is. And now what we're going to do is cross-check with our knowns. So you can see we've got to flush it out and make sure there's nothing left behind. So our first one we're going to put in is potassium. Okay. You can see you've got that beautiful purple colour. Okay, and we'll flush that system out. Holding on a little bit there. Okay, now the next one I'm going to leave the door closed because it's bright. We have our strontium. Okay, so you can see it just going up the system. I'll open it for 5 seconds or not even that much. Really bright. So you can see we definitely don't have what our known colour or our unknown was. She's holding to that colour today. Holding it really well. So we just need to wait to make sure that the flame is completely bare of the last remnants. Otherwise, you'll get cross-contamination. E.T., what I might get you to do is to get a new lot of water for me. Thank you. All right, so we're now up to our next one, which is our copper, so our known copper sample. And you can see we've got that beautiful green colour there. Okay. And just ET's just coming back with some water for us. Thanks, ET. We need to make sure we don't use tap water because if we use tap water, there are things still in there. There we go, it's cleaning up beautifully now. All right, so now we're going to go on to our cobalt. This one gets a bit of a funky colour. It's sort of a bit like an apricot-y colour. Very nice. And now the last one, just make sure it's nice and clear, is our sodium. There you go, it's a bit bright, that one. We'll just stop blinding you. You can't do it for my eyes. All right, so can you remember the colours you've all seen? Do you need to see them once more? Are you all good? It is a pretty cool machine. Is everyone okay? Do we need to see any more colours? Oh, good. Okay, over to you, Jeremy.
Okay, so before we actually move on, I just want to ask a quick question. Just in the chat, what do you think our unknown is?
I don't want to trip you up.
Cool. Copper. There's a resounding... Yep, I'd say you might be pretty close with that one. So, Edian's just going to post a link for us in the chat. If you're not already on the KIOSC learning management system, could I get you to log in now? And once you're actually in there and in the Chemistry Unit 2 module, could you please raise your hand? Feel free to ask us for help if you need help getting in there. That is perfectly fine. Fantastic, Amelia, Alyssa, and Grady, and Olivia. Okay. Yep. Just waiting on Mia and Shonak. Shonak, sorry if I mispronounced your name. If you are on, just raise your hand for me, please. Okay. Fantastic. So, moving forward, now that we've done the actual demonstration for the AAS, I just want you to go into 2.3, the AAS quiz. I want you to start that quiz and answer the first two questions, and then after that, come back to collaborate where there'll be a poll waiting for you. But do not close that quiz because we will continue with it later. And once you're back, just let us know by answering the poll. Try not to answer the poll before you come back, please. Oh, okay. Actually, probably not that poll. Okay, we'll do another one. I know I stole your thunder, Edian, by asking that question earlier. Okay, sorry, that was my bad. Okay, Alyssa's already answered the questions. Irma, great job. Great job, Amelia. Okay. So everybody's responded, and I'm assuming everybody's answered the questions. So we are, just from the questions, we know it is copper, and there are some assumptions we might be making about our metal. The AAS can actually show colors from more than one metal. So if you have a sample that contains both copper and sodium, you might get a bit of green, but a lot of yellow, because sodium is a very dominant color within the AAS system. So now we know the byproduct of diamond mining is copper. The AAS actually confirms that the concentration of copper in the lake is 70 parts per billion. From a little bit of research, we can determine that aqueous copper is toxic to animals in doses exceeding 0.2 milligrams per liter. So now we're going to answer the final 3 questions. So answer the final 3 questions and then return for the poll. It will be up. Awesome. Sorry about that. There's a bit of a weird wording. Also, if you do need help with any of the questions navigating the system, please feel free to ask. We are more than happy to help you. Some people are smashing through these quizzes. I should have made these a bit harder. Great job, Alyssa, Irma, Isabella, Mia, and Noah for doing it. Oh, we'll just wait for a few more to answer before we move on. Okay, sorry, I started talking before. Okay. So, a few of you have picked 0.7 milligrams per liter, and a few of you picked 0.13 milligrams per liter. The questions are worded a bit differently. So, the correct answer is 0.07 milligrams per liter in this case. On the LMS, it might be a bit different. It might not be. You can now submit your quizzes if you like, if you haven't already, if you've completed them. So we're going to move on to the next part. But before we do, does anybody want to let me know if they think the mining company is at fault or if they aren't? They aren't at fault. Yeah, I mean, they might not be, but I think that would be the most correct answer at the moment. So, they aren't, but they do need to be aware of the problem. That's exactly right. Companies do need to be aware of potential problems they are creating. So now we're looking at the 3 pharmaceutical companies. We have Peterson Corporation, they make paracetamol. We have Aston, who produces aspirin. And we have Isamont, who produces ibuprofen. All of these are common pain relief medications. Can anybody just give me a quick agree, disagree if you've ever taken any of these? Majority of you have taken pain relief medication? Yeah, that doesn't sound strange. Everybody needs Panadol if they've got a headache, which is paracetamol. So if you notice something, you'll see some common themes in these. You'll see these rings in each of these substances. If you have learnt about any of these phrases, which Eddie will post in the chat, just let me know and explain it, because this is stuff you'll actually look at in year 12. Yeah, awesome. So most of you have heard about some of these functional groups. So we've got benzene rings, we've got carboxylic acids, which are present in aspirin and ibuprofen, and we've also just got hydroxyl groups and esters. Esters are a bit of a weird one. You might see more about them next year. Okay. So, what analytical method can we use to determine organic contaminants in water? Remembering that all of these pain relief medications are organic chemicals. Just waiting on Grady, Ned, and Shelnak. Okay. So all of you picked HPLC, and that is great because that shows me that you've either done the pre-work or you're a really, really good guesser, or people sitting next to you are letting you know that it is HPLC. But either way, I'm happy as long as you know that it is HPLC. Before we go forward, what does HPLC stand for? Don't remember, no idea. That's okay. That's all good. HPLC is a bit of a weird one. It could stand for 2 things, but the one we're most concerned with is high performance liquid chromatography. Yeah, Alyssa's on the ball. Some people call it high pressure liquid chromatography. If you see it in the book, it's the same thing, but we normally just call it high performance liquid chromatography. So I'm going to pass it over to Kat now, who's actually going to do a demonstration of the HPLC machine. Take it away, Kat, if you're ready. If anybody's wondering, I actually don't give Kat time to prepare.
No, Alex is asleep. The cameraman's not on the job today. All right. So normally when you are doing some of your stock solutions and into a calibration curve and things like that, you would be doing large amounts or large volumes at school. So you would be using one of these. Who can tell me what this is? No one can tell me what this is. Yay, well done. So it is a volumetric flask. But for us with the HPLC, we will be using smaller volumes. So we'll be using one of these. So this here is a micro pipette. Has anyone used a micro pipette before? Raise your hands if you have. If you do biology, you may have to use them in there, but you do use them in chemistry as well. So raise your hand if you've ever used one of these before. Oh, good work, Jeremy. And ET, well done. Oh, well, yay. Okay, so that's all right. I'll show you how to use these first then. So what you need to do is basically understand how to hold it. So the first thing is, you see there's a little lip there, and you can grip around there. Up the top here, you've got this button, and basically this allows you to expel all the air when you push it to the first stop. So when you get to that first step, oh, we're just going for a little move. Go back. Okay, so when we get to our first step, you can see it goes down to there. I'll just move my fingers out of the way so you can see. And basically that pushes all the air out of here, and then when you've got your little tip on the end, or in this case the big one, it pushes everything out completely. And then when you go to put that liquid somewhere else, you push it all the way down to the bottom. That's what we call our second stop, all the way down to the bottom there. And that pushes everything out. Now when you put that into your container, you need to make sure it's pushed all the way down to the bottom, and then you don't release it while it's in there, otherwise you'll start sucking everything in. The other thing is at the top of the knob here, you pull this up, and this is how you can control the amount that you have in there. So I'm just going to let Alex zoom in so we can see it. Which way am I going? There we go. So you can see we can zoom around and make it whatever amount we want. In this case, I'm going to be doing a blank, and I need to make it 900. That's right, not 100. So we're going to be putting in our 900 microliters. So the first thing I do here, and you'll see that I have all my tips here. I have all my samples here labelled. I have my water, and then I have a stock solution here, which is our unknown aspirin, and we're going to be pouring it into here in just one moment. So find that first stop, go into the liquid, draw it up. You can see it's drawn up. That's 900 microliters. I'm going to put that into my 0 because we're just having water in our first one, sorry. Then the last button, which is pretty cool, is our eject one, and you simply push this on the side here. I can get it in the camera. There we go. And you simply eject it there. So for our next one, we need to be using our stock solution, which ET made for me beforehand. And you'll see that I have both my beakers labelled. Because it's clear liquids, you need to make sure you are labelling everything, otherwise it gets a bit confusing. Now in this case, I need to get 3 microliters, so I need to use the little guy here, and he has a little tip that goes on. I'm going to be putting 3 microliters in, just like we did before, first stop, into our first one. Now 3 microliters really isn't that much. It's 30, my apologies. And we're going to be putting that into there. So it's this tiny little amount there. And now what we need to do is top that up with our water. Okay. And it's going to be a bit of a here's one I prepared earlier, because we have all our samples already made for you, because otherwise you'll be bored sitting there listening to me go through and do all of them. So here's all the ones that we prepared earlier. We have our 0, our 3 megagrams per litre, 6, 9, 12, 15. And then we have our unknown sample that we've got from our lake. So we're going to head over to our HPLC. We're going to clean the machine, and then from there we're going to put a sample in. Watch out for the stool, you're right there. Okay. So let's get Alex into position and I'll explain the machine. So when you're ready, just let me know.
Okay.
Awesome. So here we have our HPLC. And over here is our computer where all our detected information goes to. So I'm going to get you to come around so you can show the machine. So excuse me guys, just one moment. Okay, so up the top here we have our methanol. So we've got an empty container and our full one. So the methanol makes our mobile phase. That then travels through here and then down to the bottom where we have our degasser. Now you've got to make sure that you don't have any bubbles in our mobile phase because it can actually cause problems with our column and even rupture it, which you really don't want because they're about $1,000 each. It comes up through here, gets split, and comes around to here where our injecting side is. So you get simply load it into here, then goes down to the bottom, up through the column. So this is where our stationary phase is, the column over here, and then comes around to here where our detector is. In this case, we have a UV detector. And then from there, any of the waste that isn't used through here and down into our waste container. Now, in our column here, this is where we get our separation. So because it has so much time at certain points, we get our retention time in our detector, which then determines how long a particular molecule or what it is that we get. Then we get our beautiful little line here, and then we'll get a peak which will show our area under the base and our retention time. So we're going to put in our sample, which ET's got for us here. I'll get Alex to get into position so we can show you. Already injected. Awesome. That's already injected. No. Yeah, it's already in there. What's wrong? Having a hissy fit, is it? I love HPLCs when they work.
It worked 2 minutes ago.
If it didn't work, it's okay. We got one we prepared earlier where we ran. I'm just going to stop analysis and start again. That's okay. We'll just still show them where it goes in. All right. So what happens is you have your syringe here and it's got our little sample in here. You then simply put your syringe in there and keep note on here is where another spot where our waste goes. So you simply put it in, and when enough has gone in, you can see little drops coming out. So just put that there, and then you simply eject, and then that sample then will run into our machine. Okay.
Results.
So we'll come over here and show you the results. Because it had a little hissy fit before, we just had to take a precautionary, let's have a look and make sure we can get this shown. So you can see, I'll just can't zoom in. You've got your baseline running along here, and you always will have little bits and pieces that get in the way. Then you have your beautiful peak coming up here, and then continue on. So the area under a graph will allow us to absorb, which we can calculate our concentrations from. So we'll head back over to Jeremy. He'll explain the next part.
Awesome. Thank you so much for that, Kat. That was perfect. So, sharing screen. So, Kat's just showed us HPLCs, how to use them, how they work. So I'm just going to show you, here's the data we're actually going to be using. It might look a little bit different from the data that we just saw on the screen. But that's because just in case something went wrong, we had this data as backup to that data, which was produced today. So this is your pollutant that was isolated from the rest of the organic compounds in the lake. And we're going to actually use this to determine what that pollutant is. So we know that it could either be aspirin, ibuprofen, or paracetamol. I want you to go into the modules on Collaborate, and I want you to start the 3.5 HPLC quiz. If you need help, there's some videos in the procedure HPLC page and the practical page. So when you return, there'll just be a poll on the screen for you, and that should help you. So just do the same thing, answer the first 2 questions, then come back and answer the poll. Okay, we just got a few people who still haven't answered, but for the sake of time, we'll just move forward. So yes, like any good chemist knows, concentration does affect toxicity of almost every substance. Every substance is toxic in a certain dosage, and the same is applicable to pain relief medication. So, now that we know what our pollutant is, I'm assuming you've all answered that in the quiz. It's aspirin. Okay, I didn't think I'd be giving that answer to you. And what is the toxic dose? 6,000 parts per billion. Okay, we talked about it a bit earlier. HPLC separation. Does anybody want to take a guess in the chat about how a HPLC separates molecules? I'll give you about 22 seconds to answer this. If you're unsure, that's also okay. Just if you're unsure, that's also okay. Just let me know through your reactions if you're unsure. Maybe you're confused. Yep, no, that's okay. So a HPLC actually has a few methods of separation. In our case, we're using something called a non-polar stationary phase. I'm assuming everybody knows what polarity of molecules is. It essentially means that more non-polar molecules will want to stick to the stationary phase so they don't get dragged along with the polar mobile phase. So they actually stay in the column longer. Edien's going to post a poll, and aspirin is a polar molecule. And if we're using a non-polar stationary phase, which is the C18 column in this case, how long will the aspirin actually stay in the column, do you think? Just wait for a few more to answer the question. Awesome. So everybody's put an answer in. So for those of you that picked a short time, you would be correct. Because aspirin is polar and the stationary phase is non-polar, the aspirin actually doesn't want anything to do with that stationary phase. The aspirin's like, nope, see you later, I'm going, and just goes straight through. So it's in for a short time. So there are other separation mechanisms, and these are related to the size of the molecule, the ionic charge on a molecule. There are some pretty cool separation stationary phases, but obviously they cost money and we don't have access to all of them. So, how does a HPLC detect different analytes? If you're a bit on the ball, you might be able to take a guess at this one. But if you don't know, that's okay. You can just use that confused react. Anybody want to take a guess at how does a HPLC detect different analytes? Okay, I see Grady's put up a confused face, so I'm going to assume that everybody's in the same boat. Ooh, the period of time they spend in the column. So that's a good point. So it actually can't tell based on the time an analyte spends in the column. That just tells us that they're different analytes if they spend different times in the column. We actually use light. We use a wavelength detector. It does different wavelengths and shoots, a UV laser, essentially, an ultraviolet visible laser. So Shelnak's on the right track. That is exactly it. So we use a filter, we shine different wavelengths of light, and whatever light gets absorbed, each chemical is different, and we can actually use that to determine what chemical is going through. So in saying that though, we also have our mobile phase, which we have to be wary of. So we have to make sure that our mobile phase isn't going to absorb at the same frequencies as our analytes. There's some cool videos on it. You can look them up on YouTube. Just search UV vis detectors in HPLCs. I know it's a mouthful. So, we're up to the final little bit of the quiz. Oh, let's not skip too far ahead. I want you to finish answering the final 3 questions in the HPLC quiz. This one might take a bit of time because you actually have to draw the calibration curve. Once you're done with that, could you please take a picture of that and upload it onto the Canvas website, or email it to your teacher just so he can look over it, or we can look over it. You can even use a scanner, and once you've done that and come back, can you please raise your hand for me? If you do need help remembering how to construct a calibration curve, feel free to ask any questions to us, or go back to the pre-work calibration curve section. We have the first person completing. Great work, Shalnak. I'll just give you more time. I don't really want to talk while you have to draw the calibration curves. I've drawn so many and they can be painful. Hopefully everybody's getting through it all right. Probably give you another 2 or so minutes just to get through it. And remember, if you have completed it, please raise your hand. Great work, Noah. Good stuff. Just wait on a few more people, or once it hits about 12:27. Alyssa, great job. Good job. Okay, most people are getting through it now. That's great to hear. I know calibration curves can be time consuming. So if you just want to come back to collaborate, and we'll just finish up here. So now we're at the end. We're actually doing the success criteria. So today you wouldn't have used it, but you would have observed it. How the HPLC, AAS, and UVs work in determining concentrations. You know how to interpret the data briefly. You'll get to hopefully do a bit more of that in year 12, though. And you will have constructed calibration curves and used them to determine unknown concentrations. And you'll do more of that in the post work, which is a bit more focused on the actual calibration curve aspect. So with the responses, we only have 3 so far in the poll, but that's okay. Just remember that with the calibration curve that you just constructed, try and upload it to Canvas so we can actually see your work. I know it's hard now that you're back at school and all of that, but just take a photo of it, put that photo on your computer and just upload it. We would really appreciate it here. So once a few more people have answered the poll, I'll just finish up by saying that you're more than welcome to ask any questions about the content today. I know it has been a lot of information and we have gone through it fairly quickly. So any questions that you do have about any of it, feel free to ask now. And we also just have a little survey for you to complete. So Edian will post the link to the survey. And once you've done that, I will pass it back. If nobody has any questions, I would like to pass it back over to your teacher, or Kat, if Kat has anything to add.
I've got nothing else to add. Just thank you very much, everyone, for coming today. And hopefully next year we'll be able to actually have you here at KIOSC with no COVID madness going on.
Yeah, Kat, wouldn't that be a great idea?
Oh, it'd be amazing.
Yeah. Look, thank you very much to everybody in your team for allowing us to participate today. It's been a fantastic event. I said to Edian in the feed there that it's a much better idea to see the machines in action rather than try to use them through a textbook. Our class didn't really have much idea of the operation of these machines until Monday, because we didn't have enough time to do anything about them. So thank you very much. Really appreciated your work. So yeah, thanks a lot.
No worries. Thank you so much for coming today, and thank you to Jeremy.
And yes, thank you very much, Jeremy.
No, that's okay. I'll just turn off the screen share now. Okay. So, I don't have anything more to add unless anybody has questions. We still got about 15 minutes left.
Yeah, we have. We don't have to be here for that, or we don't have to be with you for 15 minutes, but I'd like to think that people would have some questions on the class.
So if you've got any questions, put on your mic, type into the chat.
Okay, so yeah, let's put in our mics if you want to have a comment to make. One of the things that they've done a lot of work on flame tests, for instance. They know they relate those flame tests to AAS quite easily. They haven't done much work in chromatography though. Therefore, they probably found it hard to understand the way that HPLC works with retention times and those sorts of things. I equate it to paper chromatography, where you've got a stationary paper phase, a mobile solvent phase, and the components of, say, a blotch of ink will stick to the paper phase more than they'll stick to the dissolved in the solvent, and therefore they'll separate first. So that's one of those things that sometimes they will find hard to understand. But I think, Jeremy, you've explained it, and Kat, you've both explained it very, very well. So thank you very much. Any questions? We're all very shy here at Geelong Lutheran College. Either that or you two are excellent teachers.
I wouldn't go that far.
Second case. Okay. Look, we won't hold you up anymore. Thank you very much for your time. Has everybody taken us calibration curves and uploaded it to the...
And if you haven't got around to doing the survey now, there's a link also on our Canvas, our elements.
Is that for...
If they haven't done the survey for us, because the survey is really important for us because we can actually see if we're meeting the students' needs, etc.
Yeah. Okay, so how many people have not done the survey yet? Where's the survey?
Links in the chat, otherwise it's in the actual LMS, so the course that the...
Okay, so the link is in the chat.
Your private message to it's to you, Ross, sorry.
What's that?
It's in a private message to you. Are you able to put it up on the actual chat?
Okay.
We'll just put it up on the actual chat now.
Right, I'll try and find that.
So there's the actual one. I just posted that link in the chat.
Awesome.
Is that for me to do, or is that for everybody to do?
So that's the student one, and there's a private one that should be sent to you for you to complete as well.
No worries.
Yeah, thank you for that, Ross. I had fun. I know it's a lot of content and it's a lot to get through, and ideally we'd like to have it in the lab so we could actually go through and have the students make up standards and do some UV Viz.
Yeah, it's not often that. Usually, it's out of semester time that I've traditionally taken kids a fairly long time ago to Deakin, out down here in Warren Ponds. That's usually at an inconvenient time for us. And to be perfectly frank, this is a far better way to do it, because we're doing it in real time now, and they can see the actual machines happening and what you're doing with them. So, yeah, in one respect, it's good to be there, but in another respect, it's good to be right here like this. Okay, so
silver linings.
Yeah, I can commend you for what you're doing.
Thank you.
All right.
Thanks for that.
No drama.
All right, if we've got no questions, we'll leave you to it so you can get them all sorted for what they need to do.
Okay, good on you. Thank you very much. I think we need to have do something about thanking.
Thank you.
Thank you.
Thanks everybody for attending, and I hope it was at least helpful.
Yeah, we're just wanting to help you guys as much as we can, because you've had a crazy, crazy year.
We have indeed. All right, I'll leave you guys to it. So thank you very much. We'll fill in the survey, and then we'll hopefully see you soon.
No worries. Thanks so much, Ross.
Bye for now. See you later.
Bye.
How do you leave? You just probably...
Just
you can just close it.
Yeah.